So, have you ever really stopped to think about how scientists know something causes something else? I mean, for sure, it's not some kind of magic, right? It's a craft. And today, we're going to open up the researcher's toolkit and look at the art of the experiment. We'll start with a question that I promise you weren't expecting.
Okay, I know it sounds like the beginning of a bad joke, but this was a real study. Back in 1969, researchers seriously wanted to know if having an audience of other cockroaches would affect how well one roach could run through a maze. Now, to answer a weird question like that, or a serious one about a new medicine, you can't just guess. You need a plan.
And that right there is the core challenge for any researcher, proving cause and effect. You have to get from a question to an actual reliable answer. And for that, you need to build a really structured test. In the world of research, we call that blueprint and experimental design.
We're going to focus on one of the most fundamental blueprints out there, the between subjects design. The main idea here is super simple. It's all about comparison. You create different, separate groups of subjects, and each group only gets to experience one version of the experiment. Then, you just compare the results between the groups.
All right, let's reach into our toolkit and pull out the first and, honestly, the most essential tool. It's the most basic, most direct way to make a comparison, the classic two-group split. This is the setup you've probably heard of. You've got your experimental group, they get the thing you're testing, let's call it the treatment. Then you have the control group, and they get, well, pretty much nothing. They're our baseline. By comparing the two groups at the end, you can see if your treatment actually made a difference. And this is exactly what the researchers did to figure out our cockroach question. A team led by a scientist named Zajance set up two groups. One group of cockroaches had to run a maze with a little audience of other roaches watching them. The other group ran the exact same maze, but they were all alone. The difference in their finish times told the scientists everything they needed to know about the audience's effect. Okay, this is such a critical question. Think about it. If one group of cockroaches was just naturally faster from the beginning, your whole experiment is worthless, right? Your results would be totally misleading. So how do you make sure you're actually comparing apples to apples? The answer is what I like to call the golden rule of experimental design. It's the power of randomness. This one principle, random assignment, is the secret sauce that makes the whole comparison valid. Random assignment is just what it sounds like. Every single subject, every cockroach, every person has an equal chance of ending up in either the experimental group or the control group. You could literally just flip a coin for each one. What this does is it magically balances everything out, all the little individual differences, fast roaches, slow roaches, so that, on average, the two groups are basically identical before you even start. And this really gets to the why of it all. As this quote puts it, when you create these fair, random groups, you're making a tiny, miniature version of the entire population. And that means whatever effect you see in your little experiment is way more likely to be a real effect that you'd find out in the big, wide world. Okay, so that two-group split is a fantastic, powerful tool, but it's kind of the basic hammer in our toolkit. Sometimes a job calls for a bit more precision, so let's look at how we can upgrade our tools. You see, that basic design can tell you if a treatment had an effect. But what if you want to know how much of an effect it had? Like, how big was the change from the beginning to the end? For that, we're going to need a different tool. And here it is, the pretest-posttest design. It's a really simple but incredibly powerful upgrade. Here's how it works. You measure your subjects on whatever you're interested in before you give them the treatment. That's your pretest. Then you give them the treatment and you measure them again. That's the post-test. This lets you calculate the exact amount of change for each person. A 2012 study on sleep is a perfect example of this. Researchers wanted to see if listening to relaxation music could help traumatized refugees sleep better. So first, they measured everyone's sleep quality. Then, they had them listen to the music for a while. And finally, they measured their sleep quality again. This let them see precisely how much their sleep had actually improved. So here's the bottom line. There's always a trade-off. That simple post-test only design, it's fast, it's easy, it doesn't take a lot of resources. But the pre-test-post-test design, while it takes more time and effort, gives you this incredibly precise measurement of change. Choosing the right tool always depends on the question you're trying to answer. But what if your question isn't a simple treatment versus no treatment kind of deal? What if you want to compare 3 or 4 or maybe even 5 different options against each other? For that, you need a multi-tool.
The multiple groups design is really just a simple expansion of what we already know. Instead of one experimental group and one control group, you might have, say, 3 different experimental groups, each one getting a slightly different version of the treatment, and you compare them all to that one control group.
Let's imagine a study looking at how hip-hop videos might affect people's attitudes. Instead of just a simple watch a video versus don't watch a video setup, you could get way more nuanced. You could have one group watch videos with sexual content, a second group watch videos without sexual content, and a third group, your control, that watches nothing at all. See? This design lets you compare the specific effects of different types of content.
All right, time for our final and most advanced tool in the kit. This one is a thing of beauty, and it's designed to solve a really subtle but super important problem in research. It's called the Solomon four-group design. So here's the tricky problem. What if the act of taking that first test, the pretest, actually changes how people react to the treatment later on? For example, if you give someone a survey about anxiety, does filling it out make them more aware of their anxiety, which then changes how they respond to therapy? This is called a testing threat, and it can seriously mess up your results.
The Solomon design is just brilliant because it uses 4 different groups to account for every possibility. Group 1 is your standard pre-test-post-test with the treatment. Group 2 tells you if people change just from taking the test twice. Group 3 shows you the treatment's effect without any influence from a pretest. And Group 4 is your pure, untouched control. By comparing all 4 of these, you can be absolutely certain that it was the treatment that worked and that the pretest didn't accidentally skew your results. A fascinating study in 2019 used this exact design to test if virtual reality could help reduce anxiety in children before they went into surgery. The researchers had to be 100% sure that any drop in anxiety was because of the cool VR experience and not just because the kids got used to the hospital after being assessed. The Solomon design was the perfect tool to let them prove it. Wow, okay, so we've gone all the way from a simple 2-group split to this complex, elegant Solomon design, but these aren't just abstract ideas for a class. These are the real tools that researchers use every day to build knowledge, and now you have a mental toolkit for understanding exactly how they do it. And really, that's the whole point. This is all about becoming a smarter, more critical consumer of information. So the next time you see some big headline about a new scientific study, don't just look at the final result. I want you to think about the blueprint. Ask yourself, how did they actually build this experiment? Because at the end of the day, the quality of any answer always depends on the quality of its design.